Hello, hello. Okay, so let's do this is going to be lesson 2.1.2. And again, I'm just going to start off by doing a little bit of review of what we just talked about yesterday. So you don't need to copy this down. Let's just kind of get your brain awake and see what's happening here. So yesterday we talked about finding the rate of change, which is an old topic, right? We know it's algebra, and it's simply the y value minus a different y value over the x minus the other x value. Okay, so that's just the rate of change. Now, if you want to find the instantaneous rate of change, okay, and this was in yesterday's lesson. This is calculus. It's calculus because what's happening is now it's a limit process, and we're taking this point x and we're moving it back towards c, right? F of x minus f of c over x minus c. And so what we're doing is we're trying to find an instantaneous slope of that function. And so we're going to take some random point x and we're going to move it down towards it to where we can find that. Okay, and this definition right here is the derivative at c. It's the limit as x gets close to c of f of x minus f of c over x minus c. Okay, this is the derivative at c. Okay, and what does the derivative mean? It's the slope of a tangent line at x equals c. Okay, and so with this skill set, we can jump right in here into the notes here. Okay, now the notes are going to talk about velocity, position, stuff like that. It definitely sounds like physics, and it is. Okay, so your calculus knowledge is definitely going to solidify your understanding of position, velocity, and acceleration. Okay, and so we'll just kind of jump in here to the definitions. The average velocity, right? That's not calculus. There's no limits there. This is just fancy notation. Delta is change. Okay, so this is the change in position over the change in time. And so we find the change in position, right? We find the position at some time and subtract the position. This not thing, this guy here is at time zero, or starting time. Let's call it that. Okay, in physics, this would be like the initial time or the initial position. Okay, all right, and then so how do we find the instantaneous velocity? Well, we just do the same thing we did before. The only thing that changes, you guys, is that we're talking about physics. So your position function is an S instead of an F. Okay, so don't let it hurt your brain that much. So, all right, we've got a position function given as this. Okay, and it's a rock, and at any given time. Well, this is just a parabola. We know it's super skinny, right? Because that coefficient of 16 speeds everything up. So let's find the average velocity. This is algebra 1. Okay, the average velocity is your change in position over your change in time. Well, what's that mean? That's the position at time 7.4 minus your starting position of time 0 divided by the change in time. How long did you go for? Well, 7.4 minus 0, right, would tell us that. Okay, so we plug in 7.4 and you get 16 times 7.4 quantity squared minus plugging in 0, we have 16 times 0 squared over, when you subtract, you just get 7.4. Okay, the calculators are good to go. So you got 16 times 7.4 quantity squared, okay, minus 0, just gives us 876.16 divided by 7.4, 118.4. Okay, so this is going to be 118.4. All right, so it's important for me, you guys, that, and it should be for you too, like, what the heck did we just do? Right? I mean, you guys are good at math. That's why you're in AP Calc. But as we go through this class together, I know it's more difficult online, but I encourage you guys to stop and ask yourself, what just happened? Okay, and you can figure this out graphically, right? You can think about this guy as a parabola. We know it's steep, okay, and we're starting at time 0, which is right there. How high is the rock at time 0? It's 0. Okay, the position is 0. Well, what happens over there at 7.4? Well, when you plug it in, right, to your function, 16 times 7.4 squared, you're up on your parabola, right here at times 7.4, you're right there, way up here at 876.16. Okay. And so what is this? Well, remember, we just found the average rate of change, which is just simply the slope. They call it a secant line. It's just the slope through those 2 points. Okay, we found the slope as 118.4 degrees. And so, yeah, this is AP Calc, but we're just doing algebra. But tying it back in with all this stuff, I think will help you kind of pull it all together. Okay, now we're going to do some calculus. Now it wants the instantaneous velocity at the rock at time 1. Well, instantaneous velocity is right up here. Okay, the instantaneous velocity at time 1 is going to be the derivative, right, of the position function at time 1. Okay, so we just got a definition there, and we'll do a lot more of this later, but the derivative of position is velocity. Okay, and so all we have to do is use our formula. It's going to be S of t minus S of what t naught, or where we wanted that, okay, divided by t minus 1. And this is the limit as t approaches 1. Okay, and we did these yesterday, so we just plug in things that we know. S of t is a function. It's equal to 16 times t squared. Minus S of 1 is just plugging in 1, okay, over t minus 1. Okay, and remember, we're supposed to be finding the limit as t approaches 1 there. All right, so let's keep going. This becomes the limit as t approaches 1 of 16t squared minus 16 over t minus 1. And our rules from chapter 1 still hold. You plug in 1, you get 0 over 0. And so you're supposed to do stuff. You're supposed to recognize that you can factor that. That's 16 times t squared minus 1 over t minus 1. This is the difference of two perfect squares. And so we have the limit as t approaches 1 of 16 times t plus 1 over t minus 1. And the t minus 1's cancel. You plug directly in, and you get 16 times 2, or 32. Okay. Okay. And just like we did before, right? What did we just do? You guys just found the velocity at time 1. How did we do that? We used the definition that the velocity is just the derivative of the position function at that time. So we plugged in, and graphically what that means, we have our same graph, right? That's just the right-hand side because time's positive. And over here at 1, we found the slope of the tangent line to be 32. And we did that by the limit process. Okay. All right, so find the instantaneous velocity at any time. Well, instead of having a time value of 1, now we're just going to plug in t sub 0. And so this is exactly the same thing. We want the derivative of the position at some time t0. And so by definition, that's S of t minus S of t0 over t minus t0. And again, that's the limit as t approaches t0. So all we did is we took out this 1 because we don't know it, and we plugged in t0. So let's go do some crazy algebra. S of t is 16t squared minus S of t naught, or t sub 0 squared, is just 16 times t sub 0 squared over t minus t sub 0. Okay, and this limit process is still there, but I'm not going to rewrite it because we got to do some algebra here. Let's take out a 16, and we got t squared minus t naught squared. Okay, and all this is exactly the same stuff. This is the difference of two perfect squares. So let's bring that limit back here. We got t going to t0 of 16 times t minus t naught times t plus t naught over t minus t naught. Okay, again, all I'm doing is factoring. These guys will cancel. And so you have the limit as t goes to t naught of 16 times t plus t naught. Well, first rule of limits, direct substitution. And so as t approaches t naught, you're going to go plug in, just like we plugged in 1 for t, we're going to plug in t naught for t. And so that equals 16 times t naught plus t naught for a final answer of 32 t naught. And so all we did is we found, look, the derivative at any time is equal to 32 times t naught. Well, so let's use this to go back and solve b. What's the derivative at time 1? Plug in time 1 there. 32 times 1 is 32. Okay. All right. So let's just get into the heart of it, which is just doing derivatives, right? So we're going to use that same exact thing. We're going to find the derivative of this function, right? They're asking me to find the instantaneous rate of change at time 2. And so you're going to say the derivative at time 2, is our formula, the limit as x approaches some value, right, of the function minus the function at that value over x minus 2. Okay, so this is all we're doing right here. And so let's clean it up and not rewrite so much stuff. F of x, it's right there. It's 2x squared minus 3x minus 2 minus, right, what's the function value at 2? Let's plug it in. 2 squared is 4. 4 times 2 is 8. Minus 6 is 2. Minus 2 is 0. So that goes away over x minus 2. Okay, so we're using the limit process as x approaches that value 2 of this difference quotient. And so that becomes the limit as x approaches 2. Let's see here. We got to factor that. And, this is one of those things, guys, that it depends on, where you're coming from. I wish I was on campus and go talk to the pre-calc and the algebra 2 honors and all them. But how do you factor, let's just do a little sidebar here, 2x squared 2x squared minus 3x minus 2. Look, you're in AP Calc, so you should be able to factor this. I get it. So you do it however you learned it. If you want a quick, easy way to do this, the way that I do it is it's called the star method. Whatever this is here, I rewrite it. So I've got 2x and I've got 2x. I multiply the outside numbers. 2 and negative 2 makes negative 4. And then this middle number here, this b value is negative 3. You're trying to come up with two numbers that multiply to get negative 4 and add to negative 3, which would be negative 4 and 1. And clearly this can't be our answer because 2x times 2x is not 2x squared. Okay, so when you have a lead coefficient that's not 1, you will always have a fraction here you could reduce. So that goes to a 1 and a 2. So I have x minus 2 times 2x, right, plus 1. Okay, you can also just do that in your brain if that's how you do it. But either way, you got to get to x minus 2 times 2x plus 1. Okay, so you factor. We said it was x minus 2 times 2x plus 1 over my denominator there, x minus 2, which cancels. Direct substitution, you get 5. Okay. And so what you guys found is you found the derivative of that function at 2. Okay. What does it mean graphically? The slope of the tangent line at x equals 2 is 5. Okay, you could say that 100 times, and that's going to do you well. Okay, so the derivative tells you the slope of the tangent line. All right, what's up with this math 8? You have to be able in the AP exam, you guys, to calculate the derivative using your calculator at a point. Super easy. You literally hit the math button, and then as you scroll down here, you can see number 8 says n deriv. If you choose that, okay, you can use this calculator to find the derivative with respect to x. All you have to do is put your function in, which is 2x squared minus 3x minus 2. And then it says, well, where do you want me to find the derivative? I want you to find it at x equals 2. Your calculator will spit out the same answer that you got, hopefully, which is a good way to know that you did it correct. Okay. All right. Let's do this next one here. So the next one, they give you a function. Most important thing in AP Calc, right? You're given a function. Circle it. That is the graph of f prime. They can switch this to be f or f double prime. And so make sure you know what they give you. If they tell you it's on a closed interval, the graph of the derivative is given. Find the equation of a tangent line, underline. What do I need? I need the derivative at the point, and I need a point. How come? Because I use point slope form. So anytime you're asked to find a tangent line, you underline it. You write this down, write down what you need, and then go answer the question. So I've got my point. I need the derivative at 2. Well, look, they gave me a graph of the derivative. So go to 2 right there. That is f prime of 2, right? Plug in 2 and you get 12. So now we know that that's 12. And so our tangent line is our y value of 6, right? Plus our slope of 12 times x minus the x value. Super easy. Okay. All right, find an equation of a tangent line. Definition, right? Underline the definition. This is what we'll do all year long. If you need a tangent line, you need the derivative at that point. So you need to find f prime of 8. And you need a point, 8 comma something. You need both of those things. This is the easy one. If you plug 8 in here, you get the square root of 16, which would be 4. So I've got my point. Now I just need the derivative, which is the tough part. Okay, let's do this the easy way. Let's use math 8. Okay, so let's practice using our calculator. You go in, you hit math 8. math 8, sorry about that. You need the derivative with respect to x of your function, which is the square root of 2x at a value of 8. And the answer is 0.25, right? Or 1/4. Okay, and so our tangent line would be the y value of 4 plus the slope times x minus the x value. Now, I totally cheated, right? I used math 8 to do that. How else could I have done that? You should do this, right? You should go up here and do it this way. Make sure you guys know how to do things by hand, because you're going to have to do that throughout the course. And so if you need the derivative at 8, that's going to be the limit as x approaches 8, right, of f of x, which is the square root of 2x, minus f of 8, which we said was 4, over x minus 8. Okay, limits, right? Chapter 1, this all goes back. Direct substitution, 0 over 0. You got to rationalize, multiply by your fancy form of 1. Okay, if you do that and you FOIL, root 2x times root 2x is just 2x. The outsides and the insides go away. I get minus 16 over x minus 8 times the square root of 2x plus 4. Clearly, you can factor out a 2 there, and you still have this stuff. Okay, these guys would cancel. Take your limit as x approaches 8 and see if it works. If you plug in, you get 2 over, this is the square root of 16 plus 4, which is 4, right? Plus 4 more is 8. So 2/8 reduces to 1/4. Was that more work? Heck yeah. And are we going to do that all year? Heck no. This is called the formal definition of the limit. You guys will hate this stuff. You'll hate me for it. I'm sorry. Right? Everyone in Calc has to go through this. Okay. And then the next chapter, we will learn derivative shortcut rules to where we will not use this limit process. Okay. So hang tough, practice your limit process. As we go through chapter 2, there's a different way to do it with the limit process. We'll do it so much you'll hate it. And then we'll learn easy shortcuts and the class gets even easier. Okay. Hope you guys are doing well. Take care.